Let's now take a look at acids, bases, and buffers. So the first thing is we're going back to that pH scale that you can see from 0 to 14. And there's a couple of things we should highlight. So I said that as you move down the pH scale, the concentration of hydrogen ions increases. And as you move up the scale, the concentration of hydrogen ions decreases. Now, a couple of other things is that a pH of 7 is actually what we term neutral, and I'll tell you why in 1 second. But a couple of things. Anything above 7, we term basic. So you could say that anything up here we term basic. Or another word is alkaline. Alkaline. And anything below this we term acidic. So any solution with a pH above 7, we term basic or alkaline. Any solution with a pH below 7, we term acidic. If it has a pH of 7, it's neutral. But what is the definition of a base and what is the definition of an acid? Well, there's a couple of things. First thing is, if you have something like hydrochloric acid, well, it's in the name. This is an acid. Now, why is it an acid? Well, it's an acid because if I were to drop this into a solution of water, what does it do? Remember, it's not just an acid, it's a salt. It's an electrolyte. So if I were to drop this in a solution, it's going to split apart to form the hydrogen ions and chloride ions. And remember, now that I've got free hydrogen ions, the concentration of hydrogen ions in this solution is going up. What does that mean? The solution becomes more acidic. So an acid is anything, I'm going to write this down, an acid is anything that donates a hydrogen ion. That's an acid. If it donates a hydrogen ion into a solution, because when we measure the pH of something, all we measure is free hydrogen ion concentration. If it's bound up as hydrogen chloride, like this, it's not going to change the pH. It has to be freed to change the pH. Now, the thing that happens once an acid, like hydrochloric acid, donates the hydrogen ions is you're left with the chloride. And this is what we call a conjugate base. You're left with a conjugate base. So then it tells us, what's a base? A base is something that can do the opposite of an acid. It doesn't donate a hydrogen ion, it actually binds to or mops up a hydrogen ion if it needs to. So chloride can do this and it can go in the opposite direction if it needs to. But a really good base is that of hydroxyl, OH. If hydroxyl comes across hydrogen ions in a solution, it's going to come together and mop up those hydrogen ions. And what are you left with? Well, the positive balances out with the negative, so there's no charge. And you have 2 hydrogen and 1 oxygen. Wait a minute, that's water. So what you end up getting is if you have a pure base like hydrogen, if you have a pure base like hydroxyl here, it's going to mop up all of the hydrogen ions. And you're left with water, which is neutral. So that starts to make sense. If you've got a solution that's just got a whole bunch of free hydrogen ions, and you mix a whole bunch of free hydroxyl, which mop it up, what's going to happen is it forms water, and water is neutral. All right. So this is an important point. Now, when we take a look at all this, what we need to take into consideration is that you don't want a whole bunch of free hydrogen ions in the body. If this happens, if you've got too many free hydrogen ions and it becomes really acidic, it's damaging. And the reason why it's damaging is because hydrogen is missing an electron. And it searches the body to try and find that electron to be neutral again. And the more hydrogen ions you have, the more scavenging is going around to try and steal those electrons. Now, where are they going to steal electrons from? Proteins. The thing you need to know about proteins, remember proteins do all the stuff in the body, proteins are surrounded by a negative charge. So hydrogen will come along and steal the electrons from protein. And what does that do? it damages the proteins. And everything in our body is made from proteins. So if your blood or fluid in the body becomes too acidic, the proteins get damaged. So we need mechanisms in the body to resist these drastic changes in pH. And that's what I want to talk about now. They're called buffers. And the most important buffer in the body is that of the bicarbonate buffer system. Let's write this down. Bicarbonate buffer system. I'll show you how this bicarbonate buffer system works. Firstly, you need to think about this. When your cells use energy when your cells use nutrients like glucose to create energy, it produces a byproduct of carbon dioxide, right? CO2. Now, this CO2 needs to ultimately be breathed out. So it jumps into our bloodstream. But our bloodstream has huge amounts of water in it. So that carbon dioxide will ultimately mix in with the water in our bloodstream. Now, when this happens, a reaction occurs and it forms this thing, H2CO3. Now, where did I make this up? Well, there's 2 hydrogen here, there's 1 carbon here, 1 oxygen, 2 oxygen equals 3 oxygen. This is called carbonic acid. Actually, I want to write it up here. This is called carbonic acid. Now, we just defined what an acid was. What does an acid do? It donates a hydrogen ion. So acids, they hate themselves. Carbonic acid hates itself. So it splits itself apart and releases a hydrogen ion. Now, what's left? Well, we're left with another hydrogen, a carbon, and 3 oxygen. But because I've stolen the positive, I'm left with a negative. Now, what we're left with is something called bicarbonate ion, which is the conjugate base in this scenario. Now, what am I showing you here? I'm showing you ultimately this. Carbon dioxide in the body can ultimately produce hydrogen ions and make your blood acidic. But the beautiful thing with this equation is it works in the opposite direction as well. It's on a seesaw, right? So, if the carbon dioxide levels in your body go up, this part of the seesaw raises and everything rolls down in this direction and you produce more hydrogen ions. So if you've got too much carbon dioxide in your blood becomes too acidic. But the great thing is hydrogen can bind to bicarbonate and this side can raise up and roll back in this direction and produce more carbon dioxide. What do you do with carbon dioxide? You breathe it out. You blow it out. Brilliant. Now, the implications of this are important. So, for example, if something happens in your body and your hydrogen ion levels raise up, everything will fall in this direction. It'll bind to bicarbonate and it'll fall in this direction, and you'll produce more carbon dioxide. And you will hyperventilate. That's breathe quickly to blow off all that acid. This happens with people with certain types of acidosis. But on the flip side, what can happen is people who can't breathe out their carbon dioxide, so they have something like emphysema, for example, they hold on to their carbon dioxide and this side goes up, which means the equation falls in the opposite direction and the acid goes up in the blood and the body can be damaged. But this buffer works to reduce the drastic changes in pH. Amazingly, this side is basically dealt with by our lungs, our respiratory system. And it shows us that in the very short term, we can manage changes to pH simply by breathing. Breathing can help manage drastic changes in pH. If it doesn't work, this side can do something and go to the kidneys. And the kidneys can allow for us to either pee out excess hydrogen ions or bicarbonate ions, or tell the kidneys to hold on to excess hydrogen ions or bicarbonate ions. This bicarbonate buffer is amazing. And if we didn't have it, we would be dead in a very short period of time. So make sure you understand it.